Hey guys, welcome to an exciting new tutorial where we take the snake game from our previous video. You can find the link in the description to the next level. This time we are diving into the fascinating world of artificial intelligence to train our snake using deep Q learning. We'll explore how to build and train an agent powered by PyTorch and artificial neural network to master the game intelligently. Whether you are curious about AI, reinforcement learning, or just want to see a snake learn some cool moves, this video is for you. So let's get started. So in this tutorial, we'll break the process into clear and manageable steps to guide you through the training of AI for our snake game. So these are the 7 steps. So in step 1, modify the game which we have built earlier to make it ready for the AI. Step 2, we'll make the replica of the snake game but with no UI. So that will be used for the efficient and fast training. Next, step 3, artificial neural network. In this step, we'll build the brain for the snake. Step 4, the replay memory, where the snake will learn from its past experiences. Then in step 5, we'll build an agent, the decision maker that powers the snake. Next, in step 6, we'll discuss about the hyperparameters, the settings that shape our AI performance. And in step 7, we'll train the agent, bringing it all together to train and see our AI in action. So by the end, you will not only understand the process, but also have your own trained AI snake to show off. So let's get started. So we'll start with modifying the game, which we had built earlier, and make it ready for the AI. So we have created a new project, PyTorch ANN Snake Game AI. And we'll start with modifying this game.py class, which I have taken from one of our previous videos, where we have built the snake game. Let's run this to make sure everything is working fine. Yeah, so this is working fine. So let's modify this class. First, I would like to create a base class for all of these global variables. So let's call it as base.py. And I'll move these two variables from here to the base class. Let's call it as self.screenSize and self.blockwidth. Okay, now let's make changes in our game.py file. So snake class will inherit from the base class. So let's import this and call the super constructor. Same with Apple. So this will also extend the base class and call the super constructor and at the end for the game class. Okay. Now the block width would be self.blockwidth. Okay. What is the second variable? Screen size. So let's search for screen size and change to self.screenSize. Okay. What else? Okay, so let's run. Okay, so everything is working fine. Now let's see what other changes are required. So no changes in the draw function, increase, move left, move right, up, down, move, no changes here. So we'll make a change here. So at present, if a snake reaches the end of the screen, it will cross over and come out from the other side. Now we want the snake to die if a snake hits the end of the screen. So we don't need this code. We'll just remove that. And let's see, in Apple class, no changes, no changes, no changes here. In the game class, let's change the caption snake game AI deep Q. Self.timer is set to 150. We can reduce it to 1 since AI is playing this snake game now, not any human. And no changes here. We'll start with length 1, snake draw, Apple, and score is 0. Chord is 0. We'll just remove this retrieve data. We don't need this. So play, set timer, snake move, draw, no changes here, no changes here. It all looks good. We can remove this. We can also remove the record here that the agent will take care. So we'll remove all of this. Next, for checking the collision, I believe we will create a new function for this. So we'll just remove all of this. We don't need save data method here. Just remove this. No retrieve data. Remove this as well. We'll not show the game over screen because AI will continuously play and learn. We'll not show this screen, so we'll remove that. What else? Let's create a new method here for checking the collision. Let's understand this. So in snake body, the block at 0th index would be head. So we'll get the head coordinates, x and y, and then we'll check it against the rest of the snake body to see if head is hitting the snake body. Also, we will check if head is crossing the screen, right? Then also the snake should die. So in these two cases, we'll return true. The collision is true, else we'll return false. And we'll call this isCollision function inside the play method. So we'll call self.isCollision. Now let's go forward. We are not showing record on the screen, so we can remove this. And we can reduce the font size since we have a smaller screen now. And let's display it in the corner rather than in the middle of the screen since we have a smaller message now, just the score. What else? We have a reset function, no changes here. Now in the run method, we can remove all of this since we won't be playing this game, AI will. So we can remove this and we can remove all of these key events. Okay. We'll keep the quit event. This is not needed here. Here we'll quit the game and call quit. We will keep the screen update event. Here we'll have self.play and display update. What else? Let's see if we need anything else. I don't think so. Let's remove all of this. We can remove all of this as well. This run method now will be called by the agent that we'll see later. Let's correct the indentation. Okay, so this looks correct to me. We'll have one more variable called game over. This will be set to false. And when collision happens, we'll set the game over to true. And in the reset, we'll reset it to false. What else? Yes, in the game method, this will take action. So this action will be passed by the agent. And based upon the action, the snake will move. That will implement later. For now, we can have a placeholder method for get next direction. Okay, I believe with this, our game class is ready for the AI. We can remove all of this unused imports. Now we are done with the step 1. The snake game is ready for the AI. Now we'll move to the step 2, that is a snake game, no UI. So why do we need this step? Creating a snake without a UI is a crucial for efficient training. It allows the AI to process game states and learn at much faster pace without the overhead of rendering visuals. Okay, so let's go back to IDE. So what we'll do, we'll create a replica of game file. Let's call it as no UI. Okay, now in this file, we'll remove everything which is related to UI. So let's start. We don't need the parent screen. We don't need this. We don't need block, just length, X and Y coordinates, direction. We do not need a draw method. Increase, move left, right. We don't need to call this draw method here. We don't need parent screen in Apple. We'll remove this. No image for Apple. No draw method for Apple. Move method. So in the game class, we don't need any of this. No user events. No timer. Nothing here. No surface. We'll just pass the length and nothing here. No draw method. Okay, we don't need this. We'll remove this as well. Anything else? Will not be displaying any score since there is no screen. Will not be passing any of this. Game over. No event type. And just simple play method here. Let's double check. Okay, we forgot to remove this. And yeah, everything looks good. We can remove the import of Pygame. So with that, we have completed the step 2. So now we have game with UI and game without UI. Now, in step 3, we'll build the brain for the snake using artificial neural network, in short, ANN. So let's understand this in bit detail. So this is artificial neural network that powers the decision making for the snake game. Now let's understand these individual layers. Let's start with the input layer. So input layer represented by these red nodes, where each node represents one feature. Okay, and these features encode the state of the snake and its environment. So basically, state of the game. So in a game, we'll have walls, we'll have food, and we'll have the snake. So all of these, like walls, snake, and food, will be represented by the features. And for this snake game, we'll have 16 features. Why 16 features? That we will see when we implement the agent class. For now, just understand that this input layer represents the state of the game, and each state will have 16 features. What are the features? The position of the snake, whether there is a danger in each direction, what is the current direction of the snake, the location of the food relative to the snake. So collectively, all these features represents the state of the snake, and we'll pass the state of the game to the input layer. So in our program, we'll have 16 nodes. These are also called artificial neurons. Now let's talk about the hidden layer. So hidden layer represented by these blue nodes in the middle. It's a simple snake game, so we'll have only one hidden layer. So this layer processes the input features using weights and biases. It applies non-linear transformation, activation functions, learn complex patterns and relationship. So for this snake game, we are going to use rectified linear unit as the activation function. In short, RELU. Now the output layer. So in our output layer, we'll have total 4 nodes. Each of these nodes corresponds to a possible action that a snake can take. So a snake can move left, a snake can move right, a snake can go up, and a snake can go down. So each node corresponds to the one direction. So total 4 nodes. So the network predicts a Q value for each action, which represents how good it is to take that action in the current state. The action with the highest Q value is selected by the agent. And every node in the input layer is connected to the every node in the hidden layer, and every hidden node is connected to the every output node. These connections have weights which are adjusted during training to minimize the loss and improve the network performance. Now let's quickly read what Wiki says about artificial neural network. So ANN consists of connected units or nodes called artificial neurons. So these are artificial neurons which loosely model the neurons in the brain. Artificial neurons models that mimic biological neurons. So these are connected by the edges which model the synapses in the brain. Each artificial neuron receives the signal from the connected neuron, then processes them and sends a signal to the other connected neuron. So for example, this neuron takes the information from the neurons here, process them and pass the information to the output layer. The signal is a real number and the output of each neuron is computed by some nonlinear function of the sum of its input called activation function. We'll create a new class here. Let's call it as agent.py. Now let's create our artificial neural network class. This will inherit from nn.module. NN stands for neural network. Okay. Now before we proceed, we need to install the PyTorch library. So we'll do pip install torch. Okay, PyTorch is successfully installed. Import torch.nn. Okay. Now let's create the constructor and we'll have state, size, and action size. Okay, so remember the state size input and the action size output. Let's call the super constructor. Now let's have fully connected layers. So we'll have two fully connected layers. So FC1 and nn dot linear state size 64 and second fully connected layer 64 to action size. So let's understand this. We have two fully connected layer which takes the input as a size of state size and the output 64. That's the number of neurons in the hidden layer 64. I'm going with 64 neurons in the hidden layer. You can try 128, 256. General practice is to choose number of neurons in the hidden layer is 2 power n, but again, there is no fixed rule. So you can try with 32, 64, 128, 256. I think it's a simple snake game, so 64 should be good enough. And the second fully connected layer, the hidden layer 64 neurons to the action size. So as I said earlier, we'll have 16 as the state size and the action size is 4. So we'll have 64 neurons in the hidden layer, 16 in the input and 4 in the output. So first fully connected layer pass the data from the 16 neurons to the 64 neurons in the hidden layer, and the second fully connected layer pass the data from 64 neurons to output layer, which is 4 neurons. Okay, so this is important to understand. So again, the state size, the size of input layer, which corresponds to the state representation of the game. Action size, the size of the output layer representing the number of possible actions that a snake can take. Okay. FC1, this is a fully connected layer with the state size as input and 64 hidden units as output. FC2, another fully connected layer with 64 inputs from the hidden layer and action size, the output. Now let's have forward pass. And this takes state as an input. So let's understand the forward pass. The forward method defines how the input data flows through the network. So this is the first transformation. The input state is passed to the first fully connected layer, FC1, which performs the linear transformation and produces the 64 features. And then the activation function. So output of FC1, the fully connected layer 1, it passed through ReLU function, rectified linear unit activation function, and then at the end, output layer. The activation features are passed through FC2, the fully connected layer 2, to produce the final value for each action. Okay. Now with that, we have successfully created the artificial neural network that is the brain for the snake. And now we are done with the step 3. Now let's move to step 4, replay memory, leveraging past experiences to enhance learning. So let's understand what that means. So replay memory. Replay memory class is designed to manage agents' memory of the game experiences. It stores the state, action, reward, next state, and whether the episode ended. Done. For each step in the game. So for each step, we store all of these information, right? So this is one experience. A tuple which contains a state, action, reward, next state, and done. Okay. So at the present state, agent takes a step. That means agent takes an action. Based upon this action, the agent will be rewarded and then it will land on the next state. And this done is to check whether the episode has ended. So again, from the present state, take an action. Based upon the action, agent will be rewarded. It could be positive reward or negative reward. Then agent lands to the next state, and this flag is to check whether the current step has ended the episode. So during the game, we store all of these experiences. An agent will learn from these experiences. So for example, let's say we have a snake here and there is an apple here. And when a snake eats this apple, we give a positive reward to the snake. Let's say plus 10. So this is one experience. And let's say this is a wall and a snake hits the wall and dies. We give the negative reward. Let's say minus 10. And the episode is done because the game is over. So this will be true. So this is another experience. So this is one positive and one negative experience. We'll store these experiences in memory and snake will learn from this experience. For example, next time there is an apple next to a snake will know that it will get the positive reward by eating this apple. And if there is a wall next to a snake will try to avoid the wall because from the past experience, the snake will know that it will get the negative reward if it hits the wall. Okay, so we store all of such experiences in memory. And agent will be trained based on these experiences. So let's create a replay memory class. Let's have a class for replay memory. Let's create a constructor. First, let's have the device. So let's understand this. This determines whether to use GPU or CPU for computation. Okay. Why? Because leveraging a GPU significantly accelerates training when it's available. So we'll check if it is available. If not, we'll default to CPU. Next, self.capacity. So this is the capacity for the memory. So capacity, this constructor will have capacity. Now self.memory. Now the constructor is done. Now let's have the push method for pushing the experiences into memory. This will take event self.memory.append event, where the event is nothing but this tuple. Also, we need to check if memory exceeds its capacity, we need to delete the old experience. So if length of is greater than self.capacity, delete self.capacity. So if memory exceeds the capacity, we delete the oldest experience. Now let's have the sampling experiences method. Let's call it as sample k. First, we need to randomly select the batch of k experiences. Okay, so experiences, and we'll use random dot sample. We have to select it from the memory, and the size is k. Now we have list of experiences, that is list of tuples, which contains state, action, reward, next states, and dones. Now we have the list of tuples, and each tuple has these 5 components. Now we need to separate these components and convert them into PyTorch tensor so that it will be compatible with neural network. So import numpy. Okay, we don't have numpy, so we need to install that. So pip install numpy. Okay, so we have it. So it is installed. Okay, as np. So now let's have these states. State torch dot from numpy. So let's understand this. So we have list of experiences. Experiences are the list of tuples, and the first component in the tuple is the state. So E of 0 gives the state, and this gives the list of all states. Now we vertically stack these states using vstack function. So this creates a structured batch of states that can be fed into neural network. Now we have this stacked numpy array, and we'll convert this into PyTorch tensor using torch.fromNumpy. Now this is necessary because PyTorch neural networks operates only on tensors. Then we'll use this float method to convert integers to float because neural network typically expects floating points. And at the end to device, this moves the tensors to appropriate device. If GPU is available, then we'll use GPU, else we'll default to CPU. So this is slightly complex. So let's understand this again with an example because this is very important. Okay, so we have the list of experiences. So this is a list. So let's say these are the list of experiences. So we have states, action, reward, next state, and done. Okay, so here we can see that states are 1, 2, 5, 6, and 9, 10 in different experiences. First, we'll extract the states, E of 0. So that's the first component in the tuple. So that will give us the list of states 1, 2, 5, 6, and 9, 10. Then we'll use vstack function to stack them vertically. So if you notice, we stack them vertically in one numpy array. Then we convert them into PyTorch tensors. Then cast to float. Then we'll move to device, GPU if it is available, else CPU by default. Okay, so let's go back to our IDE. We are going to repeat this process for all other components. So we have 5 components. So take actions, rewards, next states, and done. So actions is E1, reward is E2, next state is E3, and dones are E4. If you notice, the fifth component that is done is a boolean, not integer. So we need to convert it to integer before we call this float method. So let's do that. So we'll call s-type. So this method converts data to unsigned 8-bit integer. So this will convert true to integer value 1 and false to integer value 0. So we have made a small mistake here. So this is a list. Okay. And now we'll return states, actions, rewards, Now we are done with the sample method. So let's summarize. So first, we randomly select the k experiences from the memory. Then for each component, we'll extract it from the sample experiences, stack them into 2D NumPy array, then convert them into PyTorch tensors, then ensures that the tensor uses the floating point precision, then moves the tensor to the correct device, GPU or CPU. So at the end, we'll return states, actions, rewards, next states, and dones. So current states, take the actions, get the rewards, move it to the next states, and dones. Now we are done with the fourth step, replay memory. Okay. Now before we build the agent, let's talk about hyperparameters. Okay. So hyperparameters are tunable parameters set before the training process to optimize the performance of the model. So let's see what those parameters are. So let's have those parameters. So we can have the parameters here. Okay, so the first parameter is number of episodes. So that defines how many episodes the agent will train on. We'll start with 10,000 episodes. So the second parameter is maximum number of steps per episode. So we have 10,000 episodes, and per episode, let's say we'll have 200,000 steps. Okay, so each time the snake moves, that is one step. Okay, so per episode, a snake can move 200,000 steps. Sets the limit how long an episode can last. Next parameter is epsilon start value, and we'll start with 1. So this is the initial value for exploration-exploitation trade-off. So let's quickly brief about exploration-exploitation trade-off. Exploration-exploitation trade-off is a fundamental concept in reinforcement learning that describes the balance between two competing objectives, exploration and exploitation. The agent tries new action to discover potentially better reward or strategies. So that is exploration. And exploitation, agent uses the knowledge it already has to maximize rewards by choosing the best known action. So before we look into the example, let's understand why trade-off is important. So exploration is necessary to ensure agent doesn't miss out the better option or strategies that hasn't tried yet. Exploitation ensures the agent leverages its current knowledge to achieve high rewards efficiently. So let's understand this from the snake game perspective. Imagine an agent is playing the snake game. So exploration, the agent might move in random directions. So this is important, random directions, even if it means dying to learn how environment reacts and which moves are safe. Okay. So for example, there is a wall and the snake is here and the snake randomly chooses the direction and hits the wall, right? So with this step, snake will learn that hitting the wall is a bad move. The snake will receive the negative reward. Exploitation, the agent deliberately takes a move it knows increases its score, such as moving towards food based on the past experience. So in exploration, agent randomly chooses the direction and store that knowledge, the outcome, right? Then in exploitation, agent uses this knowledge to determine the best move. That is, should not hit the wall or move towards the food. So trade-off, why trade-off is important. Okay, these are the same points. Let's move to the next slide. Let's clear the screen. Now let's discuss about methods to handle the trade-off. Okay. First, epsilon greedy policy. A common approach where agent chooses a random action with probability epsilon and the best known action with the probability 1 minus epsilon. And over time, epsilon is gradually decreased to favor the exploitation. The second is decaying epsilon. The value of epsilon starts with high, let's say 1 for more exploration. It decays gradually to lower value 0.01, favoring exploitation as the agent gains more experience. Okay, so initially epsilon value is 1. Let's say this is the snake game and this is the snake. So initially when the epsilon value is 1, all the moves of the snake would be random. Okay, so basically a snake will randomly explore the game and store all the knowledge or outcomes from those random moves. And over the period of time, the epsilon value will gradually decrease. What that means is a snake will exploit the knowledge which he has gained through the random moves during the exploration. So again, when game begins, a snake will take all the random moves, gain some experience, and then use those experience to make better decisions. Okay, let's clear the screen. So our epsilon starting value would be 1 and the epsilon ending value 0.001. Okay, so this one. So here it is 0.01, but we'll go with 0.001. Now next is epsilon decay value. So we are going with 0.9995, rate at which epsilon decreases over time. So we'll start with 1, we'll end with 0.001, and we'll decrease with the rate 0.9995. As you can see, it will take long time to decrease the value of epsilon from 1 to 0.001. Okay, so we want the snake to explore for a much longer time before the snake starts making the decisions. Next, the learning rate. We'll go with 0.01, the step size used by the optimizer to update weights in the neural network. So this is 0.01, so we want the snake to learn very slowly. Next is mini batch size. We'll go with 100, the number of samples used in each training step. Okay, so here we have created the method sample. So the K would be 100. Okay, so we'll take in each training step, we'll take 100 experiences to train the model. So next parameter is gamma. We'll go with 0.95, the discount factor for future rewards in Q-learning. Okay. Next parameter is replay buffer size. We'll go with 100,000. That's the maximum capacity of replay memory. So the capacity would be 100,000. Next is interpolation parameter. We'll go with 0.01, the parameter for soft updates in the target network. So all of this might not be making much sense at this point of time, but trust me, when we move forward, it will all start making sense. So these are our hyper parameters. Let's initialize few more important variables. State size 16 and action size 4. So state size represents the input size of the state vector. As we have discussed here, we'll go with 16. And the output size represents the number of possible actions the agent can take. Okay, so we'll go with 4 because a snake can move in any of the 4 directions, right? So where is action size is 4. So we have created a DQ here of the max length 100, and this we will use to keep track of last 100 scores by the snake. Okay, now we are done with hyperparameters and variables. Let's go back. Now let's talk about agent. Agent will be the decision maker that will power the snake. Okay, let's go back to our IDE and create a class for agent. Let's have a constructor. It will take state size and action size. So self dot state size, self dot action size. So we have the state size, that is input size, and the output size is the action size. And now let's have the network. So we'll create 2 networks, one for local and one for target. We'll discuss that in detail as we move forward, that why would we need 2 networks. So let's have the local network. What's the name we have given here? ANN. So ANN, and we'll pass the state size and action size. We'll create another one for the target. We forgot to create the device, so let's copy it from here, here. So now we have the device. So we'll move the neural network to the specified computational device. Okay. So we'll say to and self dot device. Same thing for target network. Now let's have the optimizer. So this is the optimizer. The purpose is it optimizes the parameter, that is weights and biases of the local network using the Adam optimizer. Now Adam optimizer is a widely used for training neural network due to its adaptive learning rates and efficiency. So we have already defined our learning rate, that is 0.01, step size used by the optimizer to update weights. Now let's have the memory, and that would be replay memory. And the capacity is replay buffer size. Next is T step. So we'll initialize to 0. So I will explain this T step when we will use it. Now let's have a variable for record. We'll set to -1 at the beginning. Let's have a placeholder variable for epsilon. We'll start with -1. So at the runtime, this epsilon value will start with 1 and ends with 0.001. Okay. Now let's create the function to get the state of the game. Call it as get state, and this will take game. Now let's understand how do we get the state of the game. Before that, let's understand the state of the snake. So imagine this is the head of the snake. Okay. So just imagine these are the eyes of the snake. So snake can look up, down, right, left, and then right up, right down, and left up. So total 8 coordinates. So when a snake looks into these directions, snake has to determine whether it is safe to move to that direction. So imagine head of the snake is here. Then it's not safe to go up because snake will hit the wall. It's not safe to go right. Snake can go left and snake can go down. I know snake can move only in 4 directions, but still we will provide the diagonals information as well to the network because that will help the network in training. So imagine a snake is here and the coordinate is 0, 0. And let's say a snake moves 20 pixels in one step. So we'll provide all the 8 coordinates to the network as part of the state. So we'll provide 0, 20 and 0, -20, 20, 0, -20, 0, and then left up is -20, 20. This is 20, 20. Now we have calculated all the 8 coordinates around the snake. Next, we'll determine whether these coordinates are safe for the snake to move and provide that information as part of the state. So let's understand this with the help of an example. So imagine this is the game screen. We have a snake here. Okay, this is the head of the snake. A snake current direction is up. That means a snake is going up. Apple is here, and these are the walls. Okay, so snake representation for the snake game as a binary vector. Each element in the vector corresponds to a specific feature of the environment or a snake's current situation. Okay, and these are 16 elements. Okay, now let's break down these elements. So first, these 8 elements represents these 8 directions. So right, down, left, up, right, down, and left up. And whether it is safe to move into that direction. So that represents the first 8 elements in the state. So next 4 elements represents the direction features. This indicates the snake current direction of movement. So left, right, up and down. So left, right, up and down. And here the snake is going up since these are binaries. So we have set the third element to 1. So these last 4 elements represents the food location feature. These indicate where the food is located relative to the snake. So left, right, up and down. This is the head of the snake. Food is here. So food is on the right side of the snake. So we have set this bit to 1, and it's also in the down direction relative to the snake head. So we have also set this bit to 1. So these 16 features represents the state of the game. So again, first 8 features represents the safe coordinates for the snake to move. Next 4 features represents the current direction of the snake. And the last 4 features represents the food location with respect to snake. Now let's go back to the IDE. So first we'll get the head coordinates. So game will have the snake. Let's check that. So this is the game class. It has the snake. And in the snake, we have X and Y's for the snake body. Okay. So, so coordinate at 0th index would be head coordinates. Let's have the Y coordinate as well. Okay. So now we have head coordinates. Now let's calculate the coordinates for all of these directions. Okay. So let's do that. So we'll call it as point left, and this would be head x minus game dot block width, comma head y. So this would be the coordinates for the point in left. Now let's calculate for right. So we'll add it. Okay, so these are the 8 coordinates around the snake head. Now let's have the state of the game. So state, so game dot is danger, and we'll pass the point left. Okay, so as of now, is danger function does not exist in the game class. We'll create that in a moment. But for now, let's complete the get state function. So we'll repeat this for 8 times. And we'll pass each of these coordinates. And this is danger method will return the Boolean value true or false based upon whether this coordinate is safe for the snake to move or not. So these 8 features are the first 8 features in the state. Next 4 features for the direction of the snake. So move direction, and this is left, right, up and down. So let's check that. So game dot snake dot direction. So snake has the direction as well. Left. Okay, so these 4 are done. Last 4 for the food location. So game dot apple dot x, if it is less than head of x, that means food is in the left of snake. Okay, so now we have the food location as well with respect to the head of the snake. And now let's return the state. So return np dot array state, int. So this array method from NumPy converts this Boolean array into integer array. Okay, true values will be converted to 1 and false value will be converted to 0. So now we are done with the get state method, and this method will give the state of the game, and we'll call this method every time snake moves to get the current state. Next, we will understand why do we need two networks. So in agent class, we had created one local network and one target network. Now let's understand why do we need them. So local network versus target network. Local queue network and target queue network is a design choice in deep queue learning to improve stability and convergence of training. So in local queue network, we update the network actively during the training. And this network is used to predict the queue values for the current state. Okay. So local queue network predicts the queue value for the current state. Whereas in target queue network, the network updates less frequently than local queue network to provide stable targets. And this is used to compute the target queue values for the next state during the training. Let's understand that with an example. But before that, we'll talk about Bellman adaptation for deep queue learning. So we compute the target queue value using this Bellman equation. So this is the queue target S and A. S stands for current state and A stands for action. R stands for the reward. This is gamma, the discount factor. This is the queue network. S prime is the new state and then A is the action in the new state. So on the current state, agent takes an action A. On that action, agent receives the reward R, and then agent lands on the new state S prime. Then again, on the new state, agent can take all the possible actions, and we will pick the action that gives the maximum reward. So this is in future, in the next state, multiplied by the discount factor, which determines how much importance is to give in the future reward. The gamma value lies between 0 and 1. We generally take the gamma value as 0.9. So again, on the current state S, agent takes an action A. For that, agent receives the reward R, and then agent lands on the new state S prime. On that new state, agent can take any of the possible actions. We will pick the action that gives the maximum reward multiplied by the discount factor, added to the reward, that becomes the targeted queue value for the current state. So this is on the target network. So let's take an example. So imagine in the snake game, this is the snake, this is the head of the snake, and this is the apple. Okay, so the current state, the snake is one step away from the food. Okay, action is move up. So snake will go up. Reward plus 10 for eating the food. Next state, after moving up, snake is in the new position. So head will be at this position, right? Now Q values for S prime. So S prime is this state. Snake can go left, right, up, and down. And these are the predicted values for each action. For going down, there's a negative reward because snake will hit its own body if it goes down. So negative reward. So we'll compute the target queue for current state, which is this, and for action going up, immediate reward is R, 10. Let's say the discount factor gamma is 0.9. So we'll pick the maximum Q value for the S prime. So we'll pick the maximum among these. So that is 3.5. So we'll pick 3.5. Discounted future reward. This is multiplied by the discount factor. So this will become 3.15. So targeted Q value would be 10 plus 3.15 is 13.15. So this is how the targeted Q value is calculated. Now let's understand where the local network comes into the picture. On target queue network, we'll compute the target queue value. And on the local network, we'll compute the expected Q value. So for the same state S and for the same action, we compute the targeted Q and the expected Q both on the different network, and then we'll compute the loss. And the objective is to minimize this loss. So we backpropagate this loss to the network, and network will adjust its weight and biases accordingly. So you remember this diagram? So this is our network, right? So in the output, we'll have the expected Q values in the local network and target Q values in target network. So we'll compute the loss and we'll backpropagate that loss to the network, and network will adjust the weights and biases accordingly to minimize this loss. So let's go back to the slide. So in reinforcement learning, the target Q values is derived from Q network itself. This is the Bellman adaptation, which we just discussed. So imagine if we use only one network, then we'll have to use the same network to compute the current Q values and the next state Q values, the targets. Then network updates itself using its own rapidly changing predictions, which can lead to oscillations and divergence in Q value estimation. So oscillations using a single Q network for both action selection and target estimation can lead to overestimation of Q values. So basically you are using the same network to predict the values, and based upon the prediction, you will update and predict and update. So network will update rapidly, and that can lead to overestimation of Q values. So solution is the target Q network serves as a fixed reference for the target Q values, and it updates less frequently via soft update to ensure target values change slowly and stabilize training. So how do these networks interact? During training, local Q network predicts Q values for the current state to determine the best action or calculate loss. The target Q network predicts Q values for the next state to compute stable target Q values for loss calculation. The soft update ensures the target Q network gradually incorporate updates from the local Q network. So now we have understood that why do we need two networks and the Bellman equation. Now let's go back to IDE. Now let's create few more functions. So first we'll create a step function. So this step function controls the process of storing the experiences and trigger the learning. So what do we need in an experience is state, action, reward, next state, and done. So this function will take these components as parameter. First, we'll store this experience in memory. So self.memory.push, and this function takes an event, and an event is tuple. So here, so now we have pushed the event into memory. Now we will trigger the learning, but we will limit how often the agent updates the neural network. So we do not want that neural network updates after every step. Rather, we want it to get updated after few moves. So for example, the agent will only learn once every 4 steps instead after every step. So this balances the computation and performance. So you remember we had a variable called t step here. So we'll make use of that. So we'll say self dot t step. So here we increment the counter t step to keep track of number of steps the agent has taken, and the counter resets after every 4 steps. Now if self dot t step is 0, then we'll take sample experiences. So here we are randomly picking up the k experiences. K is equal to mini batch size, and the mini batch size is 100, the number of sample used in each training step. So we get the experiences, and then self dot learn, and we'll pass these experiences. So we have yet to implement this learn function. Next, we'll create a function get action. So get state function determines which action agent should take in a given state. Also, it balances exploration and exploitation. So remember, we had discussed the exploration and exploitation trade-off. This function will handle that. So first, this function will use the local queue network to estimate the action value for a given state. So this function needs the state for which it needs to get an action. So the get state function returns the numpy array. So first, we need to convert this numpy array into PyTorch tensor. So let's do that. So state is equal to torch dot from numpy state, then convert to float, unsqueeze, and then to self dot device. And here 0. So first we'll convert the numpy array into PyTorch tensor, then we'll convert it to float, needed for the neural network, and unsqueeze 0. So this adds a batch dimension because Q network expects input as a batch of states. Move the tensors to the correct device, GPU or CPU. So now we have the state. So now self dot local network dot eval. So what it does, it puts the Q network into evaluation mode. That means disables features like dropout and batch normalization that are only used during training. And at this step, we are not training, we are evaluating. Now with the torch dot nograd action values self dot local network, and we'll pass the state. So this torch dot no grad is to ensure that no gradients are calculated. So this saves memory and computation while we compute the action values on the local network. So now we have Q values for all the possible actions. So it would be something like list of Q values for each action. So state and action underscore 0, action 1, and so on. So in our case, the action size is 4. So we'll get 4 Q values. Now, before we do anything else, let's put back the Q network to the training mode. So self dot local Q network train. Next, we will select the action with the highest Q value. So we'll have the move torch dot max action values dot item. And with that, we are done with the exploitation part. That means agent uses the knowledge it already has to maximize rewards by choosing the best known action. So we are choosing the best known action. Now the exploration part, where agent might move in random directions to learn how environment reacts and which moves are safe. So we'll add some random moves here. So random dot int 0 to 3. So why 0 to 3? Because our action size is 4. So this will give values either 0, 1, 2, or 3. So now we have the random move, and we also have a move computed from local network. And we'll choose one of this move based on the epsilon greedy policy, which trades off between exploration and exploitation. So what we will do, if random dot random is greater than epsilon. So this function will also take epsilon as a parameter. So if greater than epsilon, then choose the move from local network, else pick the random move. And here return move. Now let's have the learn method. So this learn function is the heart of training the agent, where Q network gets updated based on the agent's experience. So this function will take the experiences, and these experiences will be used to train the network. So let's get all the individual components from this experiences. So states, let me copy it from here. Experiences. Now we will compute the target Q values using Bellman equation. So remember Bellman equation? we'll use this equation to calculate the target Q values. So first, let's calculate the predicted Q values on the next state. Call it as next Q targets self dot target network, and we'll pass the next states dot detach. So here we have passed the next state through the target network to get the predicted Q values for all the possible actions in the next state. This detach ensures no gradients are computed for these values, and this max function finds the maximum Q value for each state across all actions. So this represents the best future actions Q value, this part. And this unsqueeze method reshapes the tensor to ensure it's compatible with further computations. Next, we will compute the target Q values. So that is reward plus discount factor times predicted Q values on the next state. So Q targets rewards plus gamma into. So why this 1 minus duns? So this is to ensure that no future reward is added for the terminal states. So basically when the episode is over. Next, we'll calculate the expected Q values on the local network. Q expected. So here we pass the current state through the local network to predict the Q values for all the actions, and this gather function extracts the Q value corresponding to action taken in each step from predicted Q values. Next, we will calculate the loss. So loss. So we are using mean squared error loss function, and we'll pass Q expected and Q targets. Now self dot optimizer. So we have the optimizer initialized here. So self dot optimizer dot zero grad. So this clears the previous gradients to prepare for new update. Now we will back propagate the loss to the network. So loss dot backward. So this computes the gradients of the loss with respect to the network parameter. And then we'll do self dot optimizer dot step. So this updates the network parameter based on the computed gradients here. And now we'll call the soft update function. So next we will implement the soft update method. So remember, the soft update method ensures the target network gradually incorporates update from the local queue network. Now let's understand how soft update works. So we have a local model, the neural network actively learning. Then we have a target model, a more stable network. And we use something called interpolation parameter, a factor between 0 and 1 that controls the update speed. So we gradually update the target model, and that update speed is controlled by this interpolation parameter. So if the parameter is 1, the target model immediately copies the local model weights, that is hard update. And if you use a very small value, let's say 0.01, then the target model updates very slowly, blending in only 1% of the local model parameters at a time. And we are going to use 0.01 as the interpolation parameter value, because we want our target model to updates very slowly. And this will be the equation we'll be using. So parameters of local network multiplied by interpolation parameter plus 1 minus interpolation parameter into parameters of target network. Here we can see if we take the value 1, then 1 minus 1, so this entire part will become 0, and the target would be equal to local. So that is the hard update. And if we take interpolation parameter as 0.01, then this is 0.01 times local plus 0.99 times target. So 99% of target parameters, 1% of local parameters. So we are blending in with only 1% of local model parameters. Now let's implement the soft update method. So function soft update, and this will take local network. Target network. So for local params, so in this line, we have combined the parameters of both the networks into pairs so that they can be updated together. So for example, local parameter is W1, W2, W3, and target parameters are V1, V2, V3. Then after combining, the pairs would be W1, V1, W2, V2, and so on. Then target params dot data copy. Then we will implement this function. So interpolation parameter into local params plus. So this is the right part of the function, and then we'll copy it to target params. Now let's have few more helper functions. Okay, so we have created 4 helper methods. Now let's talk about these methods. So first we'll talk about save model. So this save model method saves the current model's weight into a specified file. So this is the file name. First, we'll check if the folder exists. If it doesn't, we create the folder. Then we'll get local network.state and then save it in the file using torch.save method. So this ensures you can save the agent's progress and reuse the model later. And what is this folder? The folder name is model under the root directory. Now let's talk about save data method. Okay. So this save data method saves the important metadata like best score, record, and current exploration rate, epsilon, into a JSON file. So this ensures the data persists between runs, so agent doesn't lose its progress or fine-tune parameters. So for example, let's say we have trained the agent for 2000 episodes, and now we want to stop the training, and we'll resume the training after some time. So that is when this save data method will be useful, because we'll be saving the metadata like record and epsilon value to a file, so that later when we resume, we'll resume from the same point where we have stopped the training. Now let's talk about retrieve data. So this method retrieves the metadata from data.json file. So save data saves the data in data.json file, record an epsilon value. This retrieve data will retrieve the data from this file and load it to self.record and self.epsilon. So this function will be called when agent resumes the training. Now the load method. Okay, so this is data. Okay, so save model method saves the current model into this file, and load method loads the model from this file into the network. So this function checks if pre-trained model file exists in the specified directory. So that is this folder. If it exists, this function loads the model weights into local network using torch.load method. And further, this method also calls the retrieve data to load the additional metadata like record and epsilon values. So these 4 methods ensure that the agent can continue from where it left off. Next, in step 7, we'll train the agent. So let's create the driver method. So if first we'll get the game object, game, and here we'll import the game from two files, with UI and without UI. Next, we will create the agent object. So agent, let's look at the constructor. Okay, so this takes the state size and the action size, which we have defined here, 16 and 4. So state size and action size. Okay, so we have a game object and agent object. Next, we'll start the training. So we have number of episodes here, 10,000. So for episode in range 0 to number of episodes. So at the start of the episode, we'll reset the game. So game.reset. We'll set the current score to 0. Let's have a variable here for the maximum score. Now the steps. So for t in range, maximum number of steps per episode. Now at each step, agent retrieves the current state of the game. So let's call it as state old agent dot get state, and we'll pass the game. So what is it complaining about? The type game doesn't have expected attribute is danger. Okay, so we have yet to create is danger method. So we'll do it after this. So we have the current state. Now we need to get the action. So action agent dot get action, and we'll pass the state. Okay, and this expects the epsilon value as well. Now let's look at the retrieve data method. So here, when agent resumes the training, we upload the epsilon value from the file. Else it is initialized to -1. So let's do one thing. Here we'll say epsilon is equal to epsilon starting value. And so in case the training is stopped in between and resumes later, then we need to make use of the epsilon value from the data.json file. So we'll check if agent.epsilon value, if it is not -1, that means training was stopped in between. So epsilon, okay, so this is epsilon agent.epsilon, and we will pass this epsilon value to get action function. Now we have the action. Now agent needs to perform this action. So perform the action. So let's say move, and we'll do move action is equal to 1. So remember, action size is 4. So action value would be between 0 and 3. And we will set that particular index to 1. So for example, if the action is 2, the move would be 0, 0, 0, 1, 2. It would be this. Now we will pass this move to game. So game dot run, and we'll pass this move. So we have yet to complete this run method, but this run method will return few informations like reward, done, and score. So we'll pass the move to this run method. Let's call it as move. So snake will make this move, and based upon the move, we will determine the reward. We'll check if the game is over and what is the current score. So we'll return this 3 information: reward, done, and score. So we'll get reward, done, and score. So after this move, we'll get the new state. So state new agent dot get state and game. And now let's train the agent. So agent dot step, and this function takes state, action, reward, next state, and done. State old, action, reward, new state, and done. Next, we will check if with this current move, the game is over. That means if done is true. If it is true, we'll break. We'll come out from this loop. So once the episode is over, we will check if we have the max score in this episode. Max score and score. Then scores on 100 episode, append score. And now let's update the epsilon value. So epsilon max of epsilon ending value, epsilon decay into epsilon. And what is the epsilon ending value? 0.001. So epsilon value will never go below that. Okay. And after each episode, we'll save the model. So we'll call save model and save data. So agent dot save data, and we will pass the max score and epsilon value. So we are saving the model. Okay, we have not used the load method. So once we create the agent object, let's call agent dot load. So this will load the model if it exists. Now let's do a print after every 50 episodes. Okay, so we have a print statement, the current episode, score on the current episode, maximum score so far, and the average score in last 100 episodes. And let's do one more thing here. So here we can restore the max score from the file. So max score, max agent dot record max score. So now we are done with the driver method. It's exciting that we are almost ready to see the snake game in action. So let's implement the remaining methods. So first one is danger method in the game class. So let's go to the game class, and here we have a method is collision. This method checks if head of the snake has a collision with rest of the body or with the screen. Is danger method will be quite similar to this method. So let's copy this method. Danger, and we'll pass a point. So here in this method, we pass the coordinates, and we'll have to check if these coordinates are safe for the snake. So basically, if head of the snake moves to these coordinates, will there be any collision or not? So let's do that. So here we get the point. So let's change this head underscore to point. And this would be point of 0, 1. So we'll check these coordinates against the snake body and the screen size. And if there is a collision, we'll return true, else we'll return false. Next, let's complete the run method. So this run method gets the move. Now we'll have to give this move to the snake. So first, let's find out the direction in this move. So let's implement this method. So this will take move. Let's have a variable called new direction and let's default it to the right direction. Now if so this method translates the given move into corresponding direction for the snake movement. Okay. So this move parameter is one hot encoded array of length 4, where if first element is set to 1, the snake will move in the right direction. If the second element is set to 1, snake will go down. If the third element is set to 1, snake will go left. And if the fourth element is set to 1, snake will go up. So this is right, down, left, and up. Right, down, left, and up. Now let's call this method. Now let's move the snake. So if dir is equal to left, self dot snake dot move left. Else if now we are done with all the methods. So we have is danger method and we have completed the run method. Okay, so what is it complaining about? Okay, so we need to return the new direction. Now let's copy these methods to our no UI file as well. So here and this part. Now let's see what else is remaining. So this run method will be called by the agent. Okay, agent expects reward, done, and score from this method. So let's do that. So we don't have rewards yet. No, we don't have rewards yet. So let's have a variable for reward. Now we need to reward the snake for the different experiences. So here, if a snake eats the apple, so let's say when a snake eats the apple, we'll give plus 10 points. So self dot reward 10. And in case of collision, negative reward. So self dot reward, let's say minus 100. So much bigger negative reward in case of collision. Now let's add very small negative reward with every move. So the negative reward ensures that the snake learns to prioritize finding the shortest path to the food. Okay. So we have score, we have reward, and we have game over, which is done. So let's return that uh, after every step. So return, the order is this. Now let's copy these changes to no UI file as well. We'll return that. Now let's check if anything else is missing. So here, game over, game over. Okay, this would be self dot game over. Let's change it here as well. We are pretty much done with all the 7 steps. Now let's make few final changes before we run the agent and see AI in action. Okay, so first we'll change the screen size. So I believe 800 is too big. Let's change it to 600. Let's have one more variable here for food location index. So we'll say max food index and self dot screen size minus self dot. Now let's make changes in the game files. So we'll go to Apple class. Yes, I don't like this hard-coded value here. So let's do max food index and max food index. Same changes in this file. So we'll go here, self dot max food index, and now let's run the agent class. Okay, so this is weird. Um, okay, we have error sample larger than population. Here, sample class. Okay, we have missed a condition here. So here, mini batch size is 100, and we'll have to make sure that memory has at least 100 experiences before we start taking samples. So if self dot memory dot memory and is greater than mini batch size. Now let's run it again. Okay, UI is not looking good. Let's check that. So in the game class here, let's close this. Screen update. This looks good. Timer is 1. And where is the update? Okay, so here we have missed pygame dot time dot clock dot tick 200 and break. Here we can see that model folder is created and we have data.json, epsilon record, and the model. Let's delete that. Okay, let's run it again. Okay, so another error, nd array, no attribute as type, this line. Okay, there's a typo here. This should be as type. np, another typo, this should be uint. Okay, let's delete the model. Okay, another issue. Q expected local network actions dtype int 64 for index. So actions. So we are getting actions from here. Okay, action can't be float value, so let's change it to long. And anything else did we miss? Let's run it again. Okay, another issue. Looks like another typo. Okay, this is data.copy. Let's delete the model. Now let's run it again. So this seems to be working now. And we are printing episode, current score, max score, and average score after every 50 episodes. And here, epsilon value 0.91. So that is why Snake is making all the random moves. So basically, Snake is exploring the environment. Let's stop that because AI will take a long time to train the agent. Let's make use of no UI classes, which we have created for this purpose. Game and okay, so now we are using game no UI. And since we have saved the model and data, we'll not have to start from scratch. Now let's run the agent. So looks like we have another issue. No attribute is danger. So looks like this function is missing in no UI. So let's copy it from here. And yeah, that function is not here. Okay. Okay, now let's run it again and hopefully it will run without any issues. Okay, so we can already see that this is much faster. We have already completed close to 2000 episodes. We can see that average score is increasing. So we have close to 3800 episodes. Average score is 2 now. The max score is 12. So that is increasing. Okay, so at 5000 episodes, the max score is 30, average score is 6. Okay, so after 5700 episodes, max score is 49, average score is 11. 6200 episodes, max score 49, average 12.78. With max score around 60, 65, average score around 30 plus, we can call it as a win. Okay, average score is 14 plus now. So at episode 7300, max score 59, average is 23.46. Let's see if we can achieve the target by 10,000 episodes. As we can notice that episodes are taking longer time now because Snake is trained and it's playing well. So average score went up to 24 and max score is 61. Okay, we have a new record, max score 73, average score 26.57. So we have reached our target after 9100 episodes. Max score is 73, average score 30 plus. So let's stop this and let's do one thing. Let's see the UI in action. So we go to agent and let's run it. Okay, so this is a trained snake. It's playing well. Okay, let's try one more thing. Um, we'll reduce the epsilon value and we'll see if we can get any better results. So where are the hyperparameters? Okay, so we are using 9995. Let's change it to 99. Now our training would be much faster. So okay, this is no UI. Let me delete this model. Delete. I shouldn't have closed the previous tab. We could have compared the results. Okay, so after 350 episodes, average score is 4. So we can see this is much faster training. Max score 39. After 450 episodes, average score is 13. Max score 44. Okay, so after 700 episodes, max score 63, average score 31. So this is much better. Okay, average score 34. So as I said earlier, you can change these hyperparameters and play around to see if you can get better results. You can also change the network. You can add more hidden layers. You can add more nodes to the hidden layer. So after 900 episodes, max score 79, average score 33. So let's stop it now. And we got maximum score of 79 and best average score 34. Now let's see the UI again, but this time we'll stop the training. So here in the driver method, let's comment this and let's comment this out. So we have stopped the training and let's go to the top and enable only UI. Now let's run this. Okay, so this is looking good. The snake is trained well. And with that, we have completed the project. So thanks guys watching this tutorial on building a snake game AI with deep Q learning. I hope you have enjoyed this video. The full code is available on GitHub and I have shared the link in the description. Feel free to experiment and share your results. Do not forget to like, subscribe, and leave a comment if you have any questions. See you guys in the next video. Bye bye.